Today we'll be talking about cryptographic hash functions. And we're talking about integrity now. Cryptographic hash functions are used to provide message integrity. So message integrity, remember, means that the message has not been modified. For example, Alice has a message that she would like to send. And she would like to be sure that when the message arrives and Bob receives the message, that it has not been modified in transit by an attacker. Bob would like to know that the message has not been modified. And for that, we can use cryptographic hash functions. But first, let's talk about hash functions in general. A hash function, well, first let me clarify some terminology. So I'm going to use the little h to indicate the hash function and the capital H to indicate the hash value. And the hash value is also called just the hash or the message digest or digital fingerprint. And the hash function is a function that takes arbitrary length inputs and produces fixed length output. So, for example, the modulo operation is an example of a hash function or could be used as a hash function. 3 mod 10 is equal to 3. This large, absurdly large number, mod 10, is also equal to 3. Regardless of the size of the input, the output is a fixed length, in this case, a single digit. Because the input size is variable and the output size is fixed, hash functions are subject to the pigeonhole principle, which says when you have m items to fit into n containers where m is greater than n, there will necessarily be more than one item in at least one container. And for the hash function, this is true. This means that there will be 2 or more messages that hash to the same value. So let's say, for example, the hash value is fixed at 256 bits. Then there are only 2 to the 256 possible message digests. But the input size is not fixed, remember, so there are infinitely many inputs. The pigeonhole principle says there will definitely be 2 or more messages that hash to the same value. And a quick aside about functions. If you remember when you learned about functions, you maybe learned about the properties of injectivity and surjectivity. A function is injective if each input, each element in the domain, maps to a unique element in the codomain. No 2 elements in the domain map to the same element in the codomain. That's a function that is injective. And surjective says that every element in the codomain has at least one element in the domain that is getting mapped to it. But for our purposes, we want to talk about a property that functions that are injective. A hash function is not injective because 2 or more inputs will map to the same output. Because it is not injective, it is not invertible. For a hash function, there is no inverse function that undoes the function. This is because the inverse would not be a function. The inverse would look like this, right? Where one input would map to 2 outputs. So here in this image on the left, the purple the purple circles are the digests and the squares represent the preimage. One digest maps back to more than one preimage, right? So this is not a function. Okay, so hash functions do not have an inverse function. And this means that how a hash function is used in a protocol is different than, say, how we see or we saw encryption and decryption using a protocol. So here we have Alice. Alice has a message. She computes the hash function of that message to produce capital H and sends capital H to Bob. This is sort of analogous to how we saw, Alice might encrypt a message and send the ciphertext to Bob. And then Bob would take this capital H and maybe compute the inverse hash function to recover the message. But there is no inverse hash function, we've said, right? And so this is not the protocol. This is not how it works. Instead, it looks more like this. Alice computes the hash of her message, and she sends the message and the hash value to Bob. Bob then recomputes the hash value of the message using the same hash function that Alice used. So Bob receives the message and separately the hash value, and checks that his computation, Bob's computation of the hash of the message, is equal to the hash value that Alice sent on the wire. There's one more consequence of the non-injectivity of a hash function. If the hash value does not check out, Bob computes a different value than the one that Alice sent, then we know there has been some modification of the message while in transit. But if the hash value does check out, then we don't really know for sure. So let's assume for now that the attacker, for whatever reason, cannot compute the hash function on their own. So the attacker may be able to modify the message, but the tag, the hash value sent on the wire, would remain unchanged. The pigeonhole principle tells us that there are likely two messages that hash to capital H, the hash value, and maybe the attacker is able to modify the message such that it hashes to the same hash value, H, that Alice sent. For example, if the hash function is modulo 256, so for a binary value, the last byte is kept as the hash value, the attacker can easily find another message that will produce the same H, the same hash value. The attacker just has to make sure that the last byte, the least significant bits, are the same as the original message. And then Bob would never be able to detect that the attacker had in fact modified the message. So a hash can detect modification, but cannot prove the absence of modification. The key to making this work for our purposes for providing integrity is in using message digest functions, hash functions, for which accidental or even malicious modifications to the message are unlikely to produce a match. And for that, we turn to cryptographic hash functions. And a cryptographic hash function is a hash function with these three properties. And I'm listing these properties in order of increasing strength. So the hash function must be pre-image resistant, it must be second pre-image resistant, and it must be collision resistant. So let's talk about collision resistance first. This is the strongest property. This says that it is hard for the attacker to find two messages, let's say M and M prime, such that they are not equal, M does not equal M prime, and the hash of these two messages is equal. So the hash of M equals the hash of M prime. This is what it means to be collision resistant. And a cryptographically secure hash function is collision resistant. It has to have this property. Okay, the next property is second preimage resistant. And this says that given one message, let's say M, it is hard to find some other message M prime not equal to M, such that the hash of M is equal to the hash of M prime. So here the attacker has less freedom to work with, right? The attacker is given the first message and must then find another message M prime unequal to the first one, but that will produce the same hash. So here, this property is not as strong of a property. When we talk about a hash function that is second preimage resistant, that hash function is not as strong as a hash function that is collision resistant. Because this hash function, the one that is second preimage resistant, is secure against a weaker attacker, secure against a constrained attacker, an attacker that is not free to choose two messages, an attacker that is given one message and then must find a second message with a hash that will collide. Okay, and then the third property is preimage resistant. So here, let H be the hash value of some message. For the attacker, given H, it is hard for the attacker to find some message, M prime, such that the hash of M prime is equal to H. And it might be helpful to the attacker to know the message. And in this scenario, the attacker does not see the first message. The attacker just gets to see the value H. So here, in preimage resistance, the attacker, again, is even further constrained, has less information than they do in the second preimage attack, right? And so here the attacker has less power. A hash function that is only preimage resistant is not as strong as a hash function that is second preimage resistant or collision resistant. Okay, and one thing to note here is that the modulo function, which I had been using as an example, is clearly not even preimage resistant. Going back to our properties, I said that these properties are in increasing order of strength. If a hash is collision resistant, it is also second preimage resistant. And to see why this is so, if a hash function is collision resistant, it implies that it is also second preimage resistant. Consider, if that were not the case, consider if you had a hash function was second collision resistant, but not second, sorry, that was collision resistant, but not second pre-image resistant, well, the attacker can find a collision then by randomly choosing some message M, just randomly generating some message M, launching the second pre-image attack, which the attacker can do, and using that to find some M prime. And now the attacker has found two M and M prime that collide, breaking collision resistance. So it is not possible that the hash function is collision resistant, but not a second pre-image. Similarly, if a hash function is second pre-image resistant, then this implies that it is also pre-image resistant for a similar type of reason. Okay, and then just one caveat here. Second pre-image resistance does not provably imply pre-image resistance, and this is because there are some corner cases. For example, it's possible to have a hash function for which there is no second pre-image in some cases. But for our purposes, we can think of the fact that something that is second pre-image, a hash function that is second pre-image resistant is pre-image resistant. Okay, and why is finding a collision easier for the attacker? It has to do with the birthday paradox. So consider the probability that you share my birthday, right? The probability that you have the same birthday I do is 1 out of 365. And that's sort of analogous to when we talk about pre-image resistance or second pre-image. But the probability that any two people in this course share a birthday is much, much higher. And that is analogous to finding a collision, any two messages that will collide. So these are the probabilities of a birthday collision. So if you have 5 people in a room, the probability of any two people sharing a birthday is 3%. If you have 20 people in a room, the probability of any two people sharing a birthday is 41%. With 50 people in a room, the probability is at 97%. And in a class hour size, the probability approaches 100%. So these probabilities are in the attacker's favor when it comes to a collision attack. The attacker is free to choose any two messages that will collide. This is why the collision attack is the most powerful attack, and therefore why being collision resistant is a stronger property than being pre-image or second pre-image resistant. Let's talk about some particular cryptographic hash functions. The first two, MD5 and SHA-1, are being deprecated. MD5 has been deprecated. SHA-1 is being deprecated. The block size for MD5 is 128 bits, and for SHA-1 it was 160 bits. SHA-2 has two different variants, one that produces a 256-bit block and one that produces a 512-bit block. SHA-256, the variant that produces the 256-bit blocks, is a very common cryptographic hash function. And SHA-3 has multiple variants, each corresponding to different block sizes, and you don't see this one in use as much. Okay, we will stop here.